Okay, yeah, thanks very much, and thanks Thierry and Julian for inviting me. I'm yeah, slightly a fish out of water here. I'm very much not a Nemo modeler, but there's hopefully some touching on some aspects of dynamics in the North Atlantic in particular, which might be of interest. So I thought I would just give a bit of background into a bit of a sort of chronological story as to how I got interested in this question. First of all, just to provide some, I guess the sort of motivating question here is that we know from observations that the rapid array, that if we measure the overturning circulation in density coordinates or in depth coordinates, these two things are equivalent. So that means that to the north of the rapid array, water is getting denser at the same rate that it is getting deeper. So in a sense, you think there's sort of two budgets being satisfied to the north. One, that we can budget a sort of diapicnal transport budget. We also have a vertical transport budget, and we observe that these two budgets are being satisfied not only in the mean, but they're also being satisfied. There's these two metrics for overturning are synchronous at 26 north. However, we also observe from the OSNAP array that these two metrics for overturning are completely different in the subpolar North Atlantic. The rate to which water is getting denser to the north of OSNAP is much greater than the rate which is getting deeper, which is really just due to the fact that the isopycnals from east to west are sloping across the subpolar North Atlantic. So this is all quite a sort of grandiose and pretentious way of saying that it's not immediately clear where dense water sinks. And in fact, Mike Spall and Bob Pickart had a paper, had a paper a few years ago called "Why Does Dense Water Sink?" So they stole the snappy title, and I've settled for something a little bit more boring. Okay, so yeah, a lot of people have done a lot of work trying to. Okay, it's gone again. Sorry, it's back, but it's not sharing. I can still just talk just now. So there's been a lot of work on trying to sort of close the volume budget for overturning at rapid or OSNAP, mostly framed in terms of the diapicnal volume budget. So trying to marry up the overturning we measure a section with the rates of diapicnal transport to the north, but we're sort of not that satisfied of how the corresponding vertical transport budget is solved. What's the dynamical relationship there between diapicnal and vertical transport? So yeah, sort of first became interested in this question when my colleague Sam Jones was looking at this, doing this study here, which I'm just briefly going to give an overview of. Essentially, he tried to build a climatology for the temperature and salinity structure around the boundary of the subpolar gyre, following the 1,000-meter isobath, and then closed it off at some latitude here, I think it's 47 north. And in doing so, this was just looking at the climatological sort of seasonal mean conditions using Argo profiles, and by measuring, by calculating the geostrophic and Ekman velocities across the boundary, was able to generate an estimate of how, by looking at the difference in density between the water flowing into this region and out of this region, look at the rates of water mass transformation within the subpolar gyre itself. Rather than just going north of a section, we're looking for the rates of dense water formation within the subpolar gyre. And so we built this overturning stream function, which looks a bit like this. So this is much weaker than what you see for the full OSNAP array, because we're not counting dense water formation in the Nordic seas or in the Arctic. That's omitted from this by construction. And I don't want to say too much about this, there's lots in that paper, but what we found was that we found it difficult to close this vertical transport budget. We expected that within this region there should be about 12 sphere drops of sinking from the upper 1,000 meters into deeper than 1,000 meters in order to give us a kind of realistic overturning at this southern boundary of the domain. And we couldn't quite work out dynamically where that was coming from. So my colleague Alan Fox and I sort of dug into this a little bit more. In this paper in JPO a couple of years ago. So what did we do? I'm just going to close this thing here. I don't want to reboot. So we were thinking about vertical velocity and vertical transport. And we thought, well, we can generate an expression for vertical velocity at some depth, this is capital Z, by depth integrating the vorticity equation down to that depth. And we get an expression like this. So just to briefly go over these terms, we see that we have what I'm calling a barotropic term. This is due to gradients in sea surface height. I'm calling this a baroclinic term due to zonal gradients in density. A wind stress curl term, a bottom stress curl term, and that's not necessarily the curl on the seabed, but on the bottom of the volume of ocean we're considering. And then these two nonlinear terms, which are really due to the depth integral of relative vorticity advection and local vortex deformation. And in a numerical model, the subgrid scale component of these two final terms would be represented through the curl of eddy viscosity. So we use the Viking 20 model to evaluate these terms, and the terms that we evaluated from various observational data sets to try and get a handle on, well, where's this vertical velocity coming from? Dynamically, what's driving it, and how might that be related to diapycnal transport? And a nice observation is that at both rapid and OSNAP, the depth space overturning is maximal at around about 1,000 meters. And from various models suggest that this is more or less true throughout much of the North Atlantic. So with that in mind, we should be able to estimate the AMOC by accumulating vertical transport through this surface from north to south. So if you think about, this could be some section of the Atlantic here, this could be the rapid array. We know that the strength of the overturning in depth space is given by the amount of flow southwards below 1,000 meters, and just by continuity in this volume, that must be balanced by transport down into this horizontal surface at 1,000 meters depth. So we essentially evaluate this equation everywhere on this surface and then integrate from north to south to construct an overturning stream function. So we're generating a stream function here by integrating the vertical transport in latitude, whereas usually what is done is to integrate the meridional transport in depth. But because it's a stream function, those two things are equivalent. So just a quick look at some of the results we see. On the top here, these three panels are from various observational products, from satellite altimetry, from the EN4 gridded product for hydrography, and then this is ERA 5 wind stress. And then these are the corresponding fields from the Viking 20 model. So what we can see is that generally the barotropic term, it just corresponds to the meridional velocity, really, the meridional surface geostrophic velocity. So whenever the surface currents are northwards, we generally see sinking, and wherever they're southwards, we see upwelling, Eulerian upwelling. The baroclinic term kind of shows the pattern is roughly inverse to this. Maybe that's best seen in we've got a bit more resolution in the Viking 20 product. It kind of has a opposite pattern to the barotropic case. That's kind of consistent with the idea that most of these ocean currents are surface intensified geostrophic currents weakening over depth. So we see the baroclinic and barotropic contributions, as I'm defining them, kind of counteract each other to some degree over the top 1,000 meters. And then finally the surface Ekman. This is just showing us that we have Ekman suction over the subpolar North Atlantic, and Ekman pumping over the subtropics, where we go from the cyclonic to anticyclonic wind stress curl as we move from north to south. So this is really showing us that, you know, water is being sucked vertically upwards in the subpolar North Atlantic and pushed down in the subtropics. A little bit more structure here in the Viking 20 model output, and this is down to the fact that here we diagnose wind stress just based upon absolute wind speed, whereas in the model it's diagnosed based on relative wind speed relative to the ocean surface. So you can kind of see the ocean surface currents imprint themselves here on the wind stress curl field. And then for to evaluate this bottom Ekman transport term, well, we're really looking for the curl of the stress acting on the bottom of this volume in the upper 1,000 meters. But of course, when integrating that can just become a line integral along the boundary. It's really just the bottom Ekman layer transport accumulated along the 1,000 meter contour to a close approximation. So if we're looking in the observations, we estimate that from Argo trajectories in the vicinity of the 1,000 meter contour, and accumulate that going from anti-clockwise from this sort of southeast corner of the domain, moving around and down to here. What we're showing here is we're accumulating Ekman transport to the left into the domain. Here from our observational estimate from Argo trajectories, and here from the corresponding model output. And we thought this did pretty well. You know, well, not to say that the model is truth, but just to see there's a degree of agreement between the two was reassuring. About 4 spheredrops total if you accumulate everywhere to the north of 26 north. But the vast majority of that is happening in the subpolar North Atlantic, north of the Oznap array. So the regions north of the Oznap array are shown in grey here. And this makes sense because we know we have strong, very barotropic circulation in the boundary currents of the subpolar jar with a strong bottom Ekman layer. So then looking in the model, this is stuff we can, moving purely into the model now, things we can't do from observations. Looking at the actual vertical velocity field at 1,000 meters in the model, you know, diagnosed from the model velocity field. A very strong pattern of kind of mesoscale variability, lots of reds and blues, and it's not particularly obvious what the net transport is here. The pattern of, you know, integrated transport over some region is not too clear. And then this is looking at this term, the advection of relative vorticity integrated over the upper 1,000 meters. And it looks virtually the same. So we can say that, you know, locally the vertical velocity field is really dominated by this term, this advection of relative vorticity, which is perhaps not surprising because this is going to be big where we have, you know, fast-moving, eddy-rich regimes, and we can see that picking out the kind of Gulf Stream region and the boundaries of the subpolar jar here. But I guess what we're really interested in is not just the vertical velocity, but the vertical transport. How does this integrate when we start to integrate this from north to south? So this is what this, there's a lot of lines on this figure, so I apologize. This is what this figure here shows. So first of all, the black dashed line, which I've called direct, this is just the integral in the model of the vertical velocity from north to south, moving from the northern subpolar gyre down to 26 north. And we can see that, you know, we accumulate transport. By the time we get down to 26 north, we have about 15 spheredrops. This ties in with what the modelled AMOC is in over this time period. Um, now it's a bit, here I've called it remaining terms, which is a little bit misleading, but remaining terms is really this, is itself dominated by this vorticity advection term. We can see that it drives a lot of the structure. So this is this kind of pinkish line. It drives a lot of the structure in the dashed line, but it doesn't accumulate nearly as much. So we see, in the northern subpolar gyre, we have quite a lot of downwelling due to this term. And then it doesn't really do much over the mid-latitudes, and then we have a little bit of structure around about 35 north, which I suspect is due to the Gulf Stream separation. What we do see, though, is across this kind of mid-latitude band, from maybe about 55 to 35, we see this red line, this is the geostrophic term, start to contribute some downwelling. And this is purely due to the beta effect. We can have some convergence of geostrophic flow due to the beta effect. And then, yeah, a little bit, we've got some surface Ekman and bottom Ekman transports are kind of broadly in balance over the north of 55 north. And I think this kind of makes sense if we think about these boundary currents being, in a kind of long-term mean sense, accelerated by the wind stress, but being slowed down by the bottom stress. So what does this mean? Well, we have lots of sinking due to this vorticity advection term in the northern subpolar North Atlantic. And my suspicion, I suppose, is that this is really the term through which the overflows are sinking. So the dense overflows are spilling over the Greenland-Scotland ridge, and then to get down, what's in this kind of dynamical framework where we're looking at the dynamics of W, how do they actually sink? And I think it's due to this advection of relative vorticity term. Oh yeah, and then finally, so we can look at the time varying balance. So based on this integral of W over latitude and longitude, doing this integral everywhere to the north of the rapid array, we generate this estimate for the overturning at rapid, which is shown in, let me think, is shown in black is the estimate we generate, whereas grey is the observations from the rapid array itself. So we do a pretty good job of recreating it, but virtually all of this variability is just inherited from the wind stress term. So the variability is coming from the wind stress, and we have this shift in the mean because we have a lot of sinking coming from the geostrophic term, and also from these nonlinear terms near the northern subpolar boundary. And this is the same thing in the model. Looks a bit cleaner in the model, which is maybe not surprising. North of OSNAP, yeah, it's a similar story, but I have to just say that obviously from the observations we were only able to generate time mean estimates of some of these terms, so it's a bit more. The variability in our recreation, in our reconstruction, which is the black line, is more directly inherited from the wind stress. It's something to bear in mind. But if you do the same thing in the model, so this is this grey line here is the depth space overturning at OSNAP diagnosed in the model, and this black line is the integral of this all these different vertical velocity terms over the basins to the north of the OSNAP line. We get quite a nice faithful reconstruction. So that's reassuring. I suppose one thing that's sort of always never quite satisfying about this is, I set out at the start thinking, well, how does this relate to the density space overturning, or how does this relate dynamically to the diapicnal transport? which we know is what balances the density space overturning. And I'm not really sure I've got an answer to that exactly, but certainly, thinking about how can we relate this more cleanly to the large-scale density distribution in the subpolar North Atlantic. And I think the problem here is that we have this barotropic and baroclinic term, our geostrophic term, but the barotropic term is sea surface height. Now, a lot of that will be steric height, which in turn is due to density. So we're not really cleanly isolating a component that's due to the density distribution in the North Atlantic. So we're thinking about this a little bit more, and in some more recent work, we're thinking, so going back to this diagram, which is massive, I didn't realize it was going to be this big. We've got 17 sphere drips flowing southwards at this section. This is the rapid array, or any subpolar transatlantic section. We have 17 sphere drips going southwards, so we must have 17 sphere drips going down into this volume, right? That much is clear. But we don't actually have to divide it up quite like this. We could choose a slightly different volume. For example, this blue surface here, which has the same southern boundary, but rather than follow the z equals 1,000 meters surface, it gets deeper as we move to the north. And we're free to do this. So just to get rid of the grey surface now. So we now have this blue surface, which is changing in depth as we move to the north. And again, this has to obey continuity, right? The 17 sphere drips flowing out here must be flowing into this blue surface. So the reason we're thinking about this is because we think it could be advantageous to think about continuity across a surface like this. So we started thinking, this is some recent work that's still in review, about thinking about a vertical coordinate which changes with latitude according to the Coriolis parameter. So I've called it Z star, and I apologize for that because I know that in the modeling community Z star is already taken. So for now, just pretend that this is Z star, okay? I'll change it, I promise. So yeah, the idea here is we could say, well, Z star is like Z over F times some F naught, which I'm calling a reference latitude. So when F equals F naught, Z and Z star coincide, but as we move further north, F becomes larger than F naught, and our depth coordinates start to get deeper. We can see this here. So here, using a reference latitude of 26 north, we can see that our depth, our constant depth lines and our constant Z star lines coincide at 26 north, but they get deeper and fan out as we move northwards. And is this showing from the top down up here in actual map of the North Atlantic? With the darker blues here show how the surface is getting deeper as we move north. And the boundary of this surface is an F over H contour. So this is, in a sense, kind of extending the idea of F over H contours into the ocean interior. But what's quite nice, well, as I've already argued, that the transport across this blue line here, or across this blue surface, again, because we've got continuity in this volume, must be equal to the southward transport here, which is the same thing as the overturning in depth space. I want to hide this because I want to show this equation. So what I'm calling W star is the velocity across, it's essentially the velocity across this surface, the volume flux across this surface. And because it's sloping, it has a component that looks like W and a component in V. So meridional velocity will also project onto transport across this surface. So if we think about continuity in this kind of coordinate system, well, we know that W is the depth integral of the horizontal divergence. So we can plug that into our expression for W star, and then we kind of play a trick and pull this term inside the integral, so that our continuity equation kind of looks like this, which doesn't look particularly useful. But then if we consider the case where, specifically for geostrophic flow, the divergence of geostrophic flow looks like beta v over f. So if we think about, I'm going to gloss over it. I'm going to go through this quickly, but to go through the details, I'm happy to talk about it later. So from geostrophic flow, we have this definition. If we plug that into our expression for W star, we get some nice cancellations, and we end up with the W star is given by this expression, z times dv by dz, i.e. if the meridional velocity is unchanging in depth, then W star is 0. Okay, we have to have some shear in the meridional velocity for the geostrophic flow to project into flow across this surface, right? And then from thermal wind, we can write this equivalently as some stuff. It really comes down to this integral of z times d rho by dx, i.e. if density is not changing zonally, so if we have no shear, thermal wind shear in the meridional flow, then Wg star is 0. So the geostrophic component of convergence above this surface is 0. And this is really down to the fact that, well, barotropic vortex stretching, if we have a homogeneous ocean, we could think of a kind of water column here moving northwards. Well, due to planetary vorticity dynamics, that will be stretched out due to the beta effect. But then if we then bring this column back southwards again, it will shrink down again. So it can't project onto the overturning. So the barotropic flow now doesn't feature at all, and the geostrophic term is purely dependent on density. So this is quite nice, because what we really wanted to try and understand is how the Eulerian overturning at some section in the subtropics, say, is related to the density field further north. And in this framework, the geostrophic component, at least, is exactly given by the density field. We can add in the other terms again. So the total W star, I've written it slightly differently this time. I prefer it this way in my paper from 2024. If I had my time again, I'd write it differently. But so now we can kind of all our geostrophic part is wrapped up in this term now, where chi is the density is wrapped up in this chi now. Just quite a nice concise way of writing it. It's Chris Hughes's influence, and we have a term due to wind stress curl, due to bottom stress curl, which again we can think of as bottom Ekman transport along the boundary, and then this nonlinear term, which, well, the remaining stuff, which this time I'm not going to evaluate. But the same idea applies. We can construct the overturning stream function by accumulating this transport from north to south. But we have one less term than last time. We don't have what I was calling a barotropic term based on sea surface height. All the density information is now contained in this geostrophic, in this term, kind of unambiguously. This is how the ocean density field is communicated to the Eulerian overturning in the subtropics. So for this, we've only used Viking 20 because it was really trying to show how it worked in principle. The map up at the top now shows what I'm calling WG star. It looks a lot like what was previously in the vertical velocity case was WBT, barotropic part, the sea surface height part. It looks very similar, as does the wind stress curl. And the difference really being that our boundary, especially the further north we go, our boundary is different, right? 3 minutes.
3 minutes if you...
Yep. Okay. So, yeah, it's quite nice to compare the two. The nicest thing about it is that our geostrophic term now, so we're accumulating from north to south, our geostrophic term is just unambiguously a function of density, whereas previously, to get the geostrophic flow. The red line here was the sum of this barotropic term and the baroclinic term. And also in this framework, the role of geostrophic convergence seems to be bigger, particularly in the kind of northern subpolar gyre. We have the geostrophic convergence balancing to some extent the divergence due to cyclonic wind fields, and a smaller role for bottom Ekman transport. Perhaps because our boundary has moved down, it's kind of out of the rapid boundary currents of the subpolar gyre now. So that was really all I wanted to say. I wasn't going to say this. And I have some other slides which I'm going to skip over. Just very briefly, we have been doing some work completely on a tangent now about trying to do a kind of reduced version of the OSNAP line going straight from 53 North Labrador Sea across to the eastern boundary without intersecting Greenland. And due to data availability, we can get an estimate of the overturning fields going back a bit longer. But I think I've kind of run out of time, so I'll talk about anyone who's interested in that offline. And I will end there. Yeah, thanks.
Thank you very much, Neil. Nice talk. I guess there will be a few questions. Gökhan?
Yeah, I got a bit confused with your equivalency. Could you say it in plain language? What is the equivalency in depth space versus density space at OSNAP?
Well, they're not equivalent, right?
Well, in the analysis that you performed.
So, in the analysis I performed, I was comparing these vertical transport terms to the depth space overturning at OSNAP, not to the density space overturning at OSNAP. The equivalence really only exists further south, but that's just, I suppose, that's something we know empirically. It's I sort of want to, So I'm not assuming an equivalence there at OSNAP, but it is interesting to see. The dashed line here is the density space overturning at OSNAP, and the solid line is the depth space overturning. They are very coherent, and I think that's mostly just water sloshing around due to wind forcing. I think the Ekman pumping projects similarly onto both depth and density space overturning due to sort of isopycnal heave. But this is, on longer time scales, the density space overturning is a measure of diapycnal transport.
Steve?
Can you go to your slide where you introduce the Z-star coordinate? So when you write V in the final equation there, is that V oriented according to J-star, or is it V oriented according to north-south?
Horizontal, yeah. Yeah, it is.
So, I mean, you draw that as a local orthogonal coordinate over there. Do you make use of it, or is it a generalized vertical coordinate that you're using?
It's a generalized vertical coordinate. So this figure, perhaps misleadingly, has this J star in it. But here, V is oriented in the direction of J.
Fine, okay.
But I have, you can construct a locally orthogonal coordinate system by getting a Y star, which is... and I've put that in an appendix of the paper because I thought it might be interesting, but it's not immediately obvious to me.
What paper? The one that you published?
Well, no, this is in review. But I can share with you if you want. It's, I guess the advantage might be that your cross product works locally. But I don't know.
Okay, thank you.
By the way, on this slide, I was thinking, there is a nice property regarding f over h contours, which are also guidelines for waves, topographic waves.
Yeah.
What can this bring to what can this new generalized vertical coordinate can bring to the idea of vorticity dynamics with regard to topographic role?
Yeah, so that's a good question. I think need to have a bit of a think about that. I mean, one thing is we've only really been thinking about the time mean momentum or vorticity equations in this framework, and I think once you start to introduce the time varying part, think about what do Rossby waves look like in this framework. Then I'm interested to do that, but I haven't really put pen to paper on it. One thing that we did do was say, well, here I only considered the balance on one surface, and I ignored this surface here. I thought about the basically the vorticity balance depth integrated from the surface down to this blue surface, and I ignored these regions here, these shallower shelf regions. But you can just consider them as well. If you integrate down, and if the bathymetry is shallow in your surface, you just depth integrate down to the seabed. Your vorticity balance has an additional bottom pressure torque term. And then that's maybe quite interesting to think about how the shallow regions here, where you have bottom pressure torque, can communicate with the shallow regions over here, because we do have, because our depth integrated flow above the surface, this is then has one one non-divergent term, and then the other divergent term, which is purely dependent on density, is always oriented zonally. So Chris and Alan and I had a think about this, but we don't really have any real answers.
Yet.
Yeah.
Is there any question online? Oh, Mike. Before finding the answer.
Thanks for an interesting talk, Neil. When you reformulate in terms of this density, you have this integral, which I think was it the zonal derivative of the density?
Yeah.
Times z. Yes, that one. Yes.
Yeah.
So that looks very much like what you get if you're trying to calculate the MOC. Quite just sort of as a thermal wind type.
Yeah.
Quantity. So is that not no coincidence? I mean, is it essentially, is that what's happening in that formulation that you have there?
I think it's not a coincidence, but if you look at the way it's done, say at Rapid, yes, they do sort of the expression for V. They're getting expression for V really, not for W. Yes. And there is still the requirement for a barotropic reference term. When you're just looking at a slice, you're trying to get the meridional flow everywhere on a slice of constant latitude. They can integrate up the thermal wind shear. They find that it doesn't give a closed transport, or it might give some unphysical number of sphere drips going northwards. They have to impose some barotropic reference velocity to bring it back into line and isolate the overturning exchange, if you like.
So this is W at a particular latitude, isn't it? It's not an integral. Sorry, this is
W as a function of Z and a function of Y. Beta is a function of Y. So this is just and it's a function of X. Sorry, because rho is a function of X, Y, and Z.
If you integrate zonally, you get something which is proportional to the east-west pressure difference. Right?
Yeah, yeah, exactly. Yeah. So what that means is that you this WG here is showing the interior structure, but if we wanted to, when we get the total, when we integrate this in its entirety, we only need the density at the eastern and western boundaries of the domain. It collapses onto that. Yeah. I mean, or in other words, this whole thing is the horizontal curl. So when we integrate it spatially, we just need all of these terms at the boundary. So we need, this is density times grad 1 over F. We need that at the boundary. We need wind stress, bottom stress, all these terms. It's just the boundary information is sufficient. Yeah, yeah.
Questions, Mike? Yeah.
So Steve Yeager had a paper about the barotropic stream function and the vorticity analysis, and part of that paper he integrated from the surface down to a particular depth, and he used that to analyse the meridional overturning stream function. I just wonder whether you've looked at that paper and how it relates to what you're doing.
Yeah, I have looked at it. But I can't. It was a while ago, and I can't right now off the top of my head say where the differences and parallels are. There are a lot of similarities, but it's not quite the same. So yeah.
Rémi?
So just to clarify, the link that you make between W star having a closer connection to AMOC in density space relates to the equation you just showed before. But why? I mean, if you integrate zonally, as I said, it's just going to give you the transport as proportional to the east-west pressure difference, which is just say that it looks like the classical expression you get in a classical coordinate. I mean, W star is only at any given latitude is equivalent to Z, isn't it? I mean, for the Y, I don't really understand.
So I guess the real advantage is that yes, if it is just come down to the east-west pressure difference.
Yes, so I don't see the.
But the pressure field, the relevant part of the pressure field in this coordinate system is just comes down to density, if that makes sense.
But ultimately, it looks like just a classical geostrophy east-west. I mean, there is no. It's linked to the density, but you don't link it to the water mass transformation or to the diabatic modification of the density field. It's purely. I mean, you haven't really made the connection to the surface fluxes or modification of the density field.
Yeah.
So it's indirectly linked, isn't it? Oh.
It's indirectly linked. Yeah, I think there's another step there to do that. But I mean, it's we know that the light water goes northwards at the eastern boundary, and the dense water comes southwards at the western boundary. So, if we imagine that there was no dense water formation, then after some time the east-west boundary density gradient would be less, and we'd have less sinking.
You could try to repeat the same analysis by working directly in density coordinates and using the Montgomery potential. So you would have in density coordinate, your overturning would be equal to the difference in Montgomery potential. And if the slopes is not too big, you should be able to do some Taylor series expansion to link AMOC in density coordinate and Z coordinate. But the link should be done via density coordinate on Montgomery potential, because W in density coordinate is your diapiconal transport. So you might
because it can also advect. W can be the advection of isopiconals up and down. So yes,
So you need to remove the eve somehow.
Yeah, I know. I agree, and this is something I've thought about as well. And I don't. Yeah. I think it's a good point. I think that that this coordinate system gives some nice constraints when we think about the vorticity balance, and thinking about neutral surfaces and the Montgomery potential on neutral surfaces is the natural way to think about about when we're thinking about buoyancy, and potential vorticity and buoyancy are like the two constraints that the ocean is obeying, and I'm really thinking about the former, not the latter. I agree. I think there's more work to be done to really tie the two together, but I can only give a slightly hand-wavy answer here, but I'm happy to talk a bit more about it.
I got a very pragmatic question, especially for the nonlinear terms. Were you able to close the budget as accurately as needed from offline from the outputs of Viking, or did you have to rerun the model online or to compute them online?
We did a pretty good job diagnosing them offline from the 5-day mean outputs. There was always, there's always a period band missing, right, for the nonlinear terms between 5-day and the model time step, which I think is 6 seconds. We can't recover unless we're diagnosing them online. We still did a pretty good job.
Okay.
Though. Yeah.
Good. Well, are there some more questions? Otherwise, we can make a break. And if not, I would like to thank again Neil for this very interesting talk.